The next chapter here, chapter 6, chemical nomenclature. Just naming different things. These are the learning objectives here. We go through those. And then we express the composition in different ways. We're really interested in the composition of matter. Typically if we have a mixture, for mixtures we use like percent or ppm, etc. And typically these are by mass. That is, if you know the particular fertilizer is 28% nitrogen by mass, or a swimming pool chlorinating solution is 7% chlorine by mass. And so those are typically for mixtures. Those percentages will vary. But sometimes we do it by volume. Sometimes we'll look at things like alcohol solutions. Alcohol solutions are often times written as percent by volume, so 90% alcohol by volume. And then sometimes we do it by, what do you call it? Moles, which we'll talk about later. We haven't really talked, but it's very common to do it by mole or atom. And so what results is like this, a percent M over M. Do you know what M over M means? M over M just is mass. Mass of component A over total mass. So this is mass of component, mass, and so of component. And so if we're looking at percent chlorine, that would be the mass of the component chlorine. And then this would be the total mass here. So 7% chlorine by mass would be 7 grams of chlorine per 100 grams of total solution. But it doesn't matter, it could be pounds. The ratio would be exactly the same in pounds, because to convert, grams into pounds, you divide by 453.6 on both the numerator and the denominator. And so the units are, whatever units you want, kilograms, pounds, ounces, it doesn't matter what the units are, but you have to include the units. You can't just leave it blank. All right, for volume, it would look like this. Percent V over V, this would be volume of the component over, so here 90% alcohol would be, let's say, and again, it doesn't matter the units, 90 gallons of alcohol per 100 gallons, or 90 milliliters of alcohol per 100 milliliters, whatever volume unit you want. And then this one's typically written like this, percent by mole, like that. But we also have a hybrid units like this, percent M over V. One common one that's M over V percent is 0.9% sodium chloride, M over V. And the way this would be read is it would be 0.9 grams of sodium chloride per 100 milliliters of solution. Has anybody seen this before? 0.9% M over V. This is a pretty important mixture. Let me see if we can see if it pops up. I'm just doing a search for this. Yeah, you could buy this. Let's see. A lot of companies sell this. .9, except they're using W. What do you think W stands for? Weight. Weight to volume percent. This is from Granger. Granger's industrial, but this is not used industrial. This is, you know what it's used for? This is called saline solution. And this is for intravenous saline. This is intravenous saline. That they put in the little drip bottles. And so this is an important mixture used medically. Normally it's in a bag like this, 0.9% M/V. So for mixtures we usually use like a percentage or something like that. A normal saline solution. What about for substances? What do we do? Substances, we can do the same thing. For substances, we could do percent by mass. We could do percent by atom or mole. Or we could do formula. Formula is just the ratio, simple whole number ratio. Or we have actually two formulas. Actually, maybe I gotta write them here. The two formulas are this: the simplest whole number ratio. The simplest whole number ratio is called the empirical formula. Empirical formula. And so for water, what is the simplest whole number ratio for water? H2O. But for hydrogen peroxide, you know what the simplest whole number ratio is for hydrogen peroxide would be HO. And then we also have the formula for the molecule. That is the formula for the molecule. The formula for the molecule we call the molecular formula. Molecular formula. And so the example here would just be like water, H2O. This is both the empirical formula and the molecular formula. It's called the empirical formula EF and the molecular formula MF. So we don't have to write that over again. However, for hydrogen peroxide, this is H2O2, it's hydrogen peroxide. For hydrogen peroxide, the empirical formula, well, 2 to 2 is not the simplest whole number ratio. What would the simplest whole number ratio be? 1 to 1. And so the empirical formula for hydrogen peroxide is HO. The molecular formula for hydrogen peroxide is H2O2, because when we look at H2O2, that would be one molecule, which would consist of 2 atoms of hydrogen, 2 atoms of oxygen, which will use with hydrogen peroxide. It looks like this here. We don't split it. The 2 oxygens are actually bound together like this. And then you have 2 oxygens here and 2 hydrogens here. That would be the molecule, and therefore the molecular formula would represent that as well. So if you were looking at the composition of your bodies, would you use a formula to do that, or would you use probably percent composition? Yeah, because your bodies are a whole mixture of different things. Do you know what the human body would be composed of? As far as what elements?
Carbon.
Yeah, carbon,
Oxygen.
hydrogen, nitrogen. Maybe let's think of the top 6 elements of the human body. Well, I'm just curious, how would you want to represent that? What do you think would be easier to represent the composition of the human body? A percent by mass, a percent by volume, percent by atom? Well, they give different things. You know, they give you different insights into, you know, into. So is this percent by mass? We have to know, is that percent by mass or is that percent by atom? Okay, the main elements that compose the human body are shown from the most abundant by mass, not by fraction of atoms. You know? Because if we look at fraction of atoms, it's quite a bit different, you know, and we can see this. But it looks like oxygen, carbon, hydrogen, nitrogen, and others. So oxygen, carbon, hydrogen, nitrogen, calcium's up there at 1.5% of bones, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and the trace elements here. This is a percent by mass, but if we do percent by atom, it gives us a different way, and it also gives us more information about certain things. And so let's take a look at water over here. If we look at percent by mass for water, you know, water is like 88% oxygen and like 12% or 11, I should say 89% oxygen, about 11% hydrogen. Okay, that's by mass. So do you ever visualize water as being 89% oxygen, 11% hydrogen? Maybe, maybe not. For some people, I don't know. You know, but it gives you a different way of looking at water, right? Water consists mostly of oxygen by mass. But for chemists, when we look at water, typically when I think about water, I see this is going to be about 67% hydrogen and 33% oxygen. In other words, it's 2/3 hydrogen, 1/3 oxygen. This is typically the way I think about water. You know, water consists of 2 hydrogens and 1 oxygen by atoms. And so the composition of the human body, I'm very curious by atom. What atom do you think is most abundant in the human body? Carbon? Yeah, for me, it'd probably either be carbon or oxygen, or maybe hydrogen, because, you know, water. Water is the most, most, well, I don't know if that's by mass, though. A lot of people say water makes up most of your body, but is that by mass or is that by atoms? Okay. And so let's see if we have the composition of the human body by atom. But we could figure it out. Using the tools we learned in this class, we could easily convert a percentage by mass into a percentage by atom without having to look it up on Wikipedia. I'm looking it up on Wikipedia because I want to save time. I don't want to have to do the calculation. But am I going to find it? Well, how many atoms are in a human body? Do you know? I don't either. Short answer, approximately 7 times 10 to the 27 atoms in the average human body. Out of those atoms, what are they? Okay, here we go. 87% of the atoms in the human body are hydrogen and oxygen. Hydrogen or oxygen, or I don't get that. Okay, here it is. We'll look at the numbers again. it looks like the most atoms in the human body are hydrogen. So I guess water does comprise the majority of the human body. It's hydrogen. But the hydrogens are also in other parts. And then we got oxygen. Carbon's way up there. And so if you discount water, then carbon makes up most of our bodies. All right, so this is it. And then, of course, we have the formula. And so normally, do we think in terms of, when we're dealing with substances, of course, when we're dealing with mixtures, we have to deal with percentages. But when we're dealing with substances, do you usually represent substances as percentages? Either percent by mass or percent by atom? No. We usually represent substances using like, not scientifically. In other words, if somebody asks you what water is, what would you tell them? Water is H2O. That's called a formula. And so normally we represent the substances using formulas. Now we have two formulas. We have the empirical formula and the molecular formula. Which one do you think is more useful for the molecular formula? However, does everything form molecules? No, so some things are definitely going to be represented by empirical formulas, such as. Give me an example of a compound or something that does not form molecules. Copper, yeah. Copper, we use the empirical formula. The empirical formula for copper would just be a single copper atom, Cu. How about oxygen? Does oxygen not form molecules, or does oxygen form molecules? Does oxygen form molecules or not form molecules? Oxygen forms molecules, so we use the molecular formula. You know, if we were to do oxygen, what would the empirical formula for oxygen be? Oh, what would the molecular formula be? O2. What's more useful for us? O2. I mean, that's what you're breathing right now, not O. If you're breathing O, it'd be very painful because it's really reactive. And so we're breathing O2. Molecular formula is more useful. However, there's some substances that we cannot use a molecular formula for, such as iron.
No, ion.
Which one?
Ionic one? Yeah.
Ionic compounds. Yeah, you should say ionic compounds, correct. Such as? Yes, such as sodium chloride. Good. Not just ionic, but also, what's that?
No.
Not molecular. This is the third time. I'm trying to spread it out. The first time I talked about these was a long time ago, and then the second time was recent. This is the third time I'm talking about these things that don't form molecules. Instead, if they don't form molecules, what do they form typically? It doesn't have to be an element. It could be a compound. Sodium chloride is a compound. Think about this. If you could recall this quickly, you would be. And this is also what I found. You know, when I changed to how I studied, and if this last exam didn't go as well as you wanted it to go, you might consider, readjusting how you study, because that's exactly what I did. I readjusted how I studied, and then, this type of stuff. It's not because I have a good memory. I have a bad memory. It's just because I see it over and over. It's like advertising. If you're bombarded by advertising, otherwise you forget it. If you aren't hit with that advertisement, then that goes deep in your mind, you forget it. But that's why they spend billions, or I don't know how many billions, maybe even $1 trillion on advertising, because people forget. And so how do you remember? You remember by just seeing it every day. If you see it every day, you aren't going to forget it. Well, I don't want to waste any more time with it. It's lattice, ionic lattice and ionic lattice and no, but It's up to you to do. And it's not hard to, you think, that's so obscure, and the book really didn't talk about it. But if you saw it in your notes every day, if you review your notes every day, you will remember it. You would remember it. Ionic lattice and covalent lattice. The example of covalent lattice I gave you was quartz crystal was the example. However, I'll tell you, a lot of people who want to go to medical school, and there are a lot of them who want to go to medical school, will remember. It's just because medical school admission is so hyper competitive now. It's always been. In fact, if you think about medical school, what kind of memory do you have to have for that? I don't remember. But you got to have a significant, either develop it, or I don't know. We'll just come up with a system. The other systems I use, now this is very important for this chapter. When I first was learning nomenclature, they told me to write flashcards and study the flashcards. So I did that. I wrote all of them as flashcards and then studied it. But I'll tell you, when the exam came up, I couldn't write it down. I just what was that again? I couldn't write it down. And so I gave up on flashcards and doing nomenclature. You know what I did instead? I wrote it down. If I wanted to learn an ion, I'd write it down 50 times, 100 times, over and over. And then, you know what? It becomes automatic. It's like driving a car. You don't even think about it. Sulfate, boom, SO42-, because you've written it down so many times. It's so repetitive. It's in your motor memory. Motor memory. And so that's one way. When I learned nomenclature, it was all memorization, 100% memorization. But if you could learn some patterns in nomenclature, then you don't have to memorize as much. For example, if you can learn some patterns in nomenclature, you might even be able to predict certain things that you weren't required to memorize. And so you might get hit with something, that was never in the homework, that was never in the lecture, but you might be able to figure it out based on a certain pattern you might see in these things. Versus straight memorization. Straight memorization, then if it's not on the list, then you don't know it. And so anyway, we need to brush up our memory skills for this chapter. Otherwise, you're going to be suffering. And then on some people, there are some Chem 4 instructors that don't require nomenclature, which is ridiculous, unbelievable, and you're going to be in big trouble later on. And so best to start now with the memorization. And however you want to memorize, if flashcards are very effective for you, then use flashcards. Whatever method is good. Write it down. Yeah, that's what I did. But of course, what works for me doesn't necessarily work for everybody. You have to find the right system, and everybody has a different system for learning nomenclature, for memorizing information in class, that kind of stuff. But this is it's like learning a new language. You're going to have to do a lot of memorization initially. Good. Well, anyway, the chemical formula is going to be most useful for us for representing the composition of substances here. And so, formulas, we got to make sure, we capitalize things. We can't write a lowercase h because nobody will know what you're talking about. Well, people will know what you're talking about, but think that you don't know what you're talking about. NaCl, sodium chloride, talk about that. And so we have subscripts that denote the number of atoms, so 2 hydrogens, 1 oxygen. This is what we call a molecular formula. It's also an empirical formula. However, I would never call this a molecular formula. I would only call this a empirical formula. We have another name for this in general. If you don't like that term, you could use the term formula unit. Formula unit is used for both molecular, and empirical formulas. It's called formula unit. And a formula unit is for any formula. It's just a general term for formulas. General use. And so if you buy chemicals from a chemical manufacturer, oftentimes they don't want to get into the difference between a molecular and empirical. They'll just use formula unit for everything. And that way they don't have to distinguish between molecular and empirical. You're supposed to do that yourself. And so if you look at a label for any of these chemicals, they're all formula unit. And so here, water, but we need to know more detail. Water, what was this? This is both empirical and molecular. This is just empirical. Or both of those are formula units. Here, formula unit. The majority of the elements are just single atom particles, or their empirical units are single atom particles. Helium's a gas, that occurs as single atoms. Lithium, however, is a metal, and metals form what? Do the metals form molecules? Metals can form molecules, but they aren't discrete. They're called clusters. And for something that forms molecules, it should be discrete, like water. Water doesn't necessarily form clusters. Like cluster would be like H4O2, or H6O3, or H34, O17, something like that. H2O forms discrete molecules, H2O, whereas lithium can form bigger and bigger clusters, which we call tiny crystals. And those crystals can grow bigger or smaller depending on how big you want it. And so lithium forms what we call not a molecular structure, we call it we wouldn't call it, because the type of lattices that we encountered so far, ionic lattice, like salt, like sodium chloride would be an example of an ionic lattice, your typical salts or electrolytes. And then we have covalent lattices, which were like for quartz. But lithium's a metal, and so you know what we call a metallic lattice. And so it forms a metallic lattice structure. And so the empirical unit of that would be Li. So we would just say Li. There are some diatomic molecules I already asked you to memorize, right? Hydrogen, nitrogen, oxygen, fluorine, bromine, iodine. These are the 7 diatomics. So the nitrogen in the air is N2. And the chlorine gas is Cl2. It could, we could separate the atoms, the diatomic molecule, but that would require breaking them apart, which is what we call chemical separation. These are the 7 diatomics. All right, write the empirical. Write the formulas. Now, when we're writing the formula for chlorine, you got to ask: do they want the molecular formula or do they want the empirical formula? Tell me what the molecular formula for chlorine is. Cl2. The empirical formula would be argon. What's the molecular formula for argon? Is that a molecular formula? You'd say argon doesn't form molecules. That's what you tell me. There's no molecular formula for argon. Argon doesn't form molecules. Argon is just going to be Ar. Because argon exists as single argon atoms in the gas phase. And so Ar would be it. Bromine. Br2 would be the molecular. The empirical would be Br. Krypton. Krypton is Kr, and does it form molecules? No. So here it is, Cl2, Ar, Br2, Kr. all these metals form metallic lattices. All these metals here would be just the empirical unit, just a single atom. Hydrogen's here, and then the nonmetals. Okay, these nonmetals, most of them you'll represent as empirical. Like for example, silicon's what we call a semi-metal. But not all of them. So for example, sulfur. Sulfur, you have a choice. Sulfur you could either represent as the empirical unit, S, or you can represent it as a molecular unit. Do you know what sulfur forms in terms of molecules? Let's see if that's here. It forms S8. Oops.
Oh, that's a really nice.
Yeah, it's a really nice. Sulfur's really sophisticated, I tell you. Yellow sulfur. Looks like this, and the molecules it forms looks like. Looks like this. Molecule is all sulfur. It's crystalline. These are molecular crystals. And I just saw that image. Oh, this is hexa. We don't want hexa. The more common one is an 8-membered ring. This is it. And so sulfur actually forms these big molecules. These are like crowns of sulfur. The 8-membered ring of sulfur. This is what they do. In the crystal, you just pack those molecules together. And so here are a whole bunch of molecules stacked. They stack pretty neatly, even though that doesn't look so well organized. It's pretty well organized there as far as how they pack those together. They fit together nicely to form a little crystal of sulfur. And the little crystal of sulfur is going to look like this. But those we don't have to know. Like phosphorus, do you know what phosphorus forms? Phosphorus, okay, there's different. You know what isotopes are, right? You know what isotopes are. Do you know what? There's another name that sounds like isotopes, but it means something else. It's called allotropes. And so let's take a look at the difference between white phosphorus and red phosphorus. Both of these are pure phosphorus. This is like diamond. Let's compare diamond with graphite. Diamond and graphite are called allotropes of carbon. Allotropes of carbon versus isotopes. Isotopes of carbon means carbon-13, or carbon-12. Allotropes means different structures of carbon. And these are the allotropes of phosphorus. We have white phosphorus and red phosphorus. Red phosphorus is used in matches. They don't use white phosphorus matches, it's too dangerous. It's easy to oxidize, so it burns. Both white phosphorus and red phosphorus burn. White phosphorus burns in air. You don't need any match. It just starts burning. Therefore, white phosphorus is stored in underwater. Did you know that? Or in a vacuum. And so they usually store white phosphorus to prevent it from burning underwater. Like wood. If you want to prevent wood from burning, store it underwater. Will it burn? No. But you got to watch out because some things, not that you want to store all your wood underwater, but some things are reactive with water too, so you can't store them underwater. So then they use more expensive things like oil, stored under oil. Water's cheap. It's highly reactive. It's waxy. White phosphorus is poisonous. Red phosphorus is non-poisonous. Red phosphorus is less reactive. The structure is different. The ignition temperature is quite a bit different. Ignition temperature for white phosphorus is 303 Kelvin. What's room temperature about? 298 Kelvin. And so this will ignite close to, it'll be in flames, and so it's glowing. At room temperature it's glowing because it's ready to go. Ignition temperature for red phosphorus is 543. You know what this tells me? The bond. The only difference is how these things are bonded together, how the atoms are connected. Well, how they're connected is totally different. White phosphorus is molecular phosphorus, and it consists of P4 molecules, P4. Red phosphorus is a lattice type structure, but not a perfect lattice. It's a polymeric lattice type structure. And so let's take a look at the structure here. Structure of phosphorus. Oh, this is a good slide. So you can see the difference. White phosphorus forms these 4 atom cages. We call them a cage. These aren't that stable. It's dangerous. However, red phosphorus forms these long chains. These long chains are called polymer type chains. Polymer. And so you see this is called a monomer. And the monomer just keeps repeating to form a polymer. It just goes on. So there's no distinct beginning and end here. So instead we use the molecular formula or the empirical formula for this. So for red phosphorus we always use just P. For for white phosphorus, however, or this is also called yellow phosphorus, we could use P4. This is molecular. But people don't get it. When you go through the homework, most of the time you'll see yellow sulfur, S. White, it doesn't matter if it's white or red. Phosphorus, P. You aren't expected to get into it in that much detail, but this is what you do if you were expected to get into it. More detail. Well, how do you know all this stuff? Well, you just learn little bits here, little bits there, and then you just build up knowledge that way. You build up little bits here, little bits there. Pretty soon the books get thicker and thicker. If you look at some of the books, like chemistry books from a century ago, they're pretty thin. And the books get just bigger and bigger and bigger. Because it's just they want to put more and more information. So what they're trying to do is they're trying to give you years, not years, but decades worth of knowledge and then just try to cram it into one semester. Which is great because can you imagine if you had to learn chemistry and it took you decades? The pace was that slow. It'd be torturous.
Slow progress.
Yeah. Instead, what they're going to do is force feed it into you right now with this book, but it's better than the alternative, I think. Well, anyway, so we're going to learn. First, we're going to learn how to name elements. The naming of the elements, are you guys working on the memorization for and the symbol, the formula, the composition? The composition will all pure. And we just have to distinguish, when we're doing the elements, we only have to distinguish between if it's molecular or, for elements, there aren't going to be ionic. It's either going to be molecular or not molecular, i.e. empirical. And so all we need to do is figure out, do we write the molecular formula or the empirical formula for the element? Now we go to compounds. Well, can you tell me what a compound is and what the difference between a compound and an element is? Yeah, two or more elements chemically bonded together, combined, like water. You know, water is a compound. And so when we look at it, we have binary molecular compounds. So we're going to break down the rules into molecular compounds versus something called ionic compounds versus covalent lattice type compounds. And so we have different types of compounds, and the way we name them varies. And so this is called binary molecular. Binary, do you know what that means? Two. Yeah. Compounds formed by two non-metal elements, or by a metalloid and a non-metal pair. So non-metal means that we just have to go to the periodic table and take a look. If we have two elements combining in this yellow region, then we're going to use the binary molecular. If it's in the green, then it's a trade-off. If we have a blue and a yellow, then use the rules for ionic compound nomenclature, which we'll talk about. If it's green and yellow, then it's bordered. We could either use either system. And so we have some systems developed. And so let's take a look at some binary molecular compounds first. And, binary, a lot of these you already know how to name. For example, CO2. Well, carbon, non-metal. Oxygen, non-metal. But isn't it two? This is three atoms I have. This is 1, 2, 3 atoms. Can I still call it binary? Or should I call this trinary? I still call it binary because even though it's 3 atoms, it's two different elements. Yeah. This is what we call a binary molecular compound. Versus this. Could I call this a binary molecular compound? No. This is not a binary. This would be, let's say, after bi should be tri. So these rules don't work. These rules are only valid for binary. And so let's look at binary molecular compound. Well, how do I know it's molecule? Well, how I know it's a molecular compound is just a guess. You know, it's not always 100% accurate. But most of the time, when you have two nonmetals bonded together, most of the time, two nonmetals I'll just say two nonmetal compounds are molecular. But not always. So you probably already know the name of this. What is it? Carbon dioxide. Okay, the thing to note is this, di and ide. You know, this is carbon, so that's normal, but oxygen has changed. You know, this is oxygen. And so to say that there are two oxygens is the di, and the ide means it's the second element. So we change the ending of the second element. Second element ending has changed to I. Use the IDE suffix. IDE. That's all we do. And so let's use the rules to name some of these things here. Like Water is its common name. You know, H2O is water. Water is what we call the common name. This based on historical precedent. Everybody calls it water. However, you know, common, I guess, or traditional, I think we call it traditional name. AKA common name. Common name's the actual term used for it. Common name. What would you name this using the binary, you know, like carbon dioxide? How would we name water? Yeah, we call water dihydrogen because there are two hydrogens. Dihydrogen. Monoxide. So di here, and then mono here for one. And then we could call it monooxide or monoxide. What sounds better to the ear? Monooxide or monoxide? So what we're going to do is we're going to drop the double vowel here and just go monoxide. And then the ending. So oxygen's name has been modified quite a bit, just so it sounds better. So dihydrogen monoxide. Dihydrogen monoxide. I told you about dihydrogen monoxide, right? Did I tell you about dihydrogen monoxide? Yeah.
Should I get rid of it?
Yeah. DHMO, we call it.
Deadly.
DHMO. Where did they ban it? I want to know what city it was banned in. Oh, they nearly fell for it. I thought they fell for it. Aliso Viejo. There's a city in Northern California that I think they did issue some resolution, city resolution banning it.
It's okay, the plants are gonna die.
Yeah. Oh, that's good. Anyway, let's go back to this. You know, I was trying to buy some, what's that, NH3? NH3 is called NH3 is called ammonia. And so I went into did I tell you this already? I went to a chemical catalog and I was looking for ammonia. I couldn't find ammonia. And I thought, this is ridiculous because ammonia is such a common chemical. Why can't I find it in this catalog? And then I finally found it. Like, wasted a lot of time looking for it. And I finally found it. It wasn't called ammonia. It was called nitrogen hydrogen, but hydrogen it would be not hydroxide. This would be nitrogen, tri is correct. Then hydrogen, so you could call it trihydrogenide or trihydrogenide. Does that sound good? Yeah, maybe let's drop it. Keep dropping vowels until it sounds right. If we keep dropping vowels until it sounds right, then trihydride is it. So it comes out to nitrogen trihydride. I couldn't find it, and so I'm guilty of that as well, not realizing the names. So DHMO, that was a big thing for a while because the DHMO was in the news quite a lot. But we have to learn some of these prefixes. The prefixes would be the number. So mono we know, di we know, tri we know. 4 is then 5, 6, 7. 7, you know, a lot of people That one's a little bit tricky. 8, 9 is a little bit tricky. Nona. 10 is pretty straightforward. Deca. So you have to memorize these. But by far the most common of these ones here, maybe tetra, penta. These ones over here are less common. Nona. In fact, you know what? I don't think I've ever used nona in a binary molecular compound, but you might as well just know it because it's like, okay, I know all the numbers except for 9, you know, from 1 through 10. And so you probably never use it. Go ahead and learn it. So let's do this. What we're going to do is we're going to go back and forth. So this is the name, and then we want to write the formula. What is the formula for dinitrogen pentasulfide? N2S5. Good. Is that a empirical formula? This is an empirical formula. Is this a molecular formula? We don't know because we don't know what the molecule looks like. If we knew what the molecule looks like, then we can say, yes, it's a molecular formula. We need to know what the molecule is in order to determine if that's the molecular formula or not. But I think it is. Let's try the next one. Dinitrogen. Here it would have been pentaoxide, but they dropped the A. It's called pentoxide. Dinitrogen pentoxide. N2O5. All right. These are very similar. I wish they gave us some more variety here. Okay, what's next? Name that for me. Oh, you know I said I never use nona except for this slide. This is the only time I ever used nona.
Can you go back to the table?
Can we go back to the table? Yeah. All right, I409. I409. I is what? Iodine. Tetraiodine. Okay, so that would be tetraiodine. Yeah, nonoxide. Okay. Tetraiodine nonoxide. Yeah. Tetraiodine nonoxide, and then the last one, PF5. Phosphorus. No, francium is FR. F is fluorine. We're going to have to change it to fluoride. Yeah. So this would be phosphorus pentafluoride. So let's check our answer. Dinitrogen pentasulfide is N2S5, N2O5. We get the tetraiodine nonoxide, and then we have phosphorus pentafluoride. Note the spelling on fluorine. A lot of people misspell it and call it flour, fluorine, or fluoride, because it's FLU, not FLO, FLU. So,
Do you always have to change the prefix to I?
Yeah, you always have to change the ending here to I. For all of these, do you see it?
Sure.
The second one's always going to be I. Well, let me throw in another example here.
These rules only apply for the binary molecular compounds?
Yeah, these are for binary molecular compounds. You know, most of binary. How do you recognize if it's a binary molecular compound? Like, for example, this. Is this a binary molecular compound? Yeah. Well, one, is it binary? Yes. Is it made up of nonmetals?
Yes.
Check. So Made up of nonmetals is binary, so it must be a binary molecular compound, but there's one problem, and do you see the one problem? It's that plus sign. That plus sign means it's a charge, so we don't call it, this would not be considered a binary molecular compound. It's close. If it was missing that charge, then yes. But with that charge, no. With that charge, what we call it is an ion, and we have a whole different set of rules for that. And so, it's crazy, so something like this, NH4NO3, people will start doing this. Okay, nitrogen, tetrahydrogen, mononitrogen trioxide. Is that how you'd name this? No. But why? Because this is not a binary molecular compound. These are not binary molecular compounds, so we don't use the binary molecular compound rules. We have another set of rules for these other ones. How do we know that? Well, we got to memorize the other set of rules. This chapter is full of memorization. This particular species is called an ion. You know what ions are? Ions have a charge. Ions can have a positive charge or a negative charge. And what we see, this charge is a result of an imbalance of electrons and protons. And so we have cations that form when an atom loses an electron. When an atom loses an electron, then the positive charge is bigger than the negative charge. That result is a positively charged ion. And we have anions. Anions are negatively charged because some atoms can gain, or not just atoms, but species can gain. Okay, these are called monatomic. Monatomic, what does that mean? Monatomic.
One atom.
Yeah, monoatom. One atom. These are one atom species. This is not monatomic. You know what we call this?
Diatomic.
It's not diatomic either. Diatomic would be 2 atoms. This is 5 atoms. So we have a choice. We could call this pentatomic, or we could call it, no, when you get to 5 atoms, people stop. All right. Instead, you know what people call it? They don't call it pentatomic. Another name for it. The diatomics are no problem. Diatomics, maybe even triatomics are no problem. But once you hit triatomics, then they throw them all together. And they call them polyatomic. And so ammonium would be, well, actually, I didn't tell you the name of that, but we memorized the name of that. NH4 plus is called ammonium ion. Ammonium ion, how do I know? I memorized it. How did I memorize it? Well, I tried flashcards once, and that wasn't that effective, and then I started writing it. I must have written, when I was learning ammonium, I must have written it like 50 to 100 times, repeatedly, over. Just training. It's like, when you go to, like throwing a ball. I haven't thrown a ball in years. I can't throw a ball straight anymore because my muscles have lost that. But I can still ride a bicycle, which is good. I'm glad I haven't forgotten how to do that. This is motor memory. I still remember ammonium, NH4 plus. But if you don't use it, you tend to lose it. Yeah. So this is why the repetition is very good, because you don't use everything, but you don't want to forget it either, because you think about how much time you invested in this class. You're investing like 16 weeks worth of your life into this class. Do you want to just forget it, 3 years down the road? Just everything wiped clean? Maybe.
Just don't order H2O2.
Well, anyway, this is what we call cation, because it's got a net positive charge, so some imbalance. We don't need to know. It's just got an imbalance. We also have anion. In fact, this guy here, this is called ammonium, and that makes up half of ammonium nitrate. The other half of ammonium nitrate comes from NaO3 minus. This is a polyatomic anion. Polyatomic cations and polyatomic anions, we've memorized those. For the monatomics, there's a heck of a lot less memorization because polyatomics are more complex, but the monatomics are a lot less complex. And so for the monatomics, it's easy to remember. Rules for naming. This is too much. Let me tell you what the rules are here. Monatomic cation. The name is equal to the name of the element. And then you can add the word ion at the end. And so, for example, a monatomic, this would be an example of a monatomic cation, Na with a positive charge. What element is Na? Sodium. And so the name of this, we just call it the sodium ion. We need that ion, otherwise if we just called it sodium, we don't know if we're talking about this, Na. Na is just called sodium. And so we can call it, to be more specific, we can call it cation, the sodium cation. Or to be more specific, we could call this sodium metal. If it's metal, it's not the ion, because when you eat table salt, do you chew on chunks of metallic sodium crystal chunks in your salt? No, there are no metal chunks in your salt. If there were metal chunks in your salt, you'd probably be very worried about contamination. All right, some of the charges are higher. So, for example, what element is this?
Barium.
This is barium. And therefore, what would you call this? Now, barium has a 2+ charge, or +2 charge.
Barium.
Yeah, this is called the barium ion. Now, it gets a little bit tricky because no, diion would be you'd have something like 2 bariums together. So the charge. Instead, sometimes we do represent the charge, and so let me show you 2 of them, and then we'll take a break. What element is this? Iron. And so we call this iron metal or elemental iron. And so iron would also be called iron metal or elemental iron. Elemental iron. Now we have a confusing situation because there's only one barium ion. Unfortunately, there are 2 iron ions, one with a 2+ charge, the other with a 3+ charge. Now we can't call both of those iron ions, right? Because then we don't know which one we're talking about. Are we talking about the 2+ or the 3+? And so the first one we call iron, and we don't use the die. We use Roman numeral. We'll call this iron, and then we say this iron 2 ion, or iron 2 cation. And so it's just spelled out iron 2 ion. This one would be called iron 3. Now the Roman numeral just tells us what the charge is. So this is +2 charge on the ion. This is +3. So this is iron 2, iron 3.
Can you also say like for this, ion?
Yeah, in the old days they called this ferrous,
Yes.
and they called this one ferric. The ferrous is the lower charged. When we have the aus is lower, ic is higher. And so whenever we have multiple charges, we have different systems. Ferrium is what, the Latin word or something for iron? So that's where the symbol comes from for iron. All right, let's stop here. We'll take a break, and then we'll see, how we can determine whether it's got multiple or one. So would we call this barium 2? We would not call that barium 2. Do you know why? There's only one. And so we would not use barium 2 here. Just cross it out.